they're also asking us what is that maximum rate of change. So they're not asking us just the direction vector that will take us to the highest steepness. They're also asking us what's that value of the steepness. So number one, we want to find the gradient nabla f. That's the derivative of x e to the y. That's with respect x. That's simply e to the y. And the derivative with respect y, that's x e to the y, because the derivative of e to the y with respect y is itself times, well, this multiple constant. Well, so what else do we need to know? Well, we need to find, or to evaluate this gradient at the point 2, 0. And that's e to the 0, 2, e to the 0, which in this case is 1, 2. So that is that on the surface z equals x e to the y, standing at the point 2, 0, we need to go in the direction 1, 2 in order to go with the highest steepness. All right, now they're asking us for that value of the slope. So all we have to do is that max rate of change this will be the magnitude of that gradient at the point 2, 0. And what did we get for that? Didn't we get the vector 1, 2? So that's 1 squared plus 2 squared. That's 1 plus 4. And this is the square root of 5. So this means that the highest slope that from that point in the direction of the vector y, 2, that's going to be that slope, that steepness. All right. Let's look at another example. Well, for these few examples, we have been thinking of these surfaces like hills, like surface in which we either we go up the hill, down the hill, or just go around the circles along the level curve on the hill. But I mean, that's just to make the visualization of all this in an easier way. However, in this case, we can use this type of this tool to find, at the direction of, for example, in this case, a hot plate. We want to know in which direction is the hot. When you warm, for example, you warm a metal plate, it's not going to be evenly hot at all points. And so at some points it might be hotter than another point. So suppose we have this temperature function 20 minus 4x squared minus y squared, and x and y are measured in centimeters, and they're telling us in what direction from the point 2, -3 does the temperature increase most rapidly, and what is that rate of decrease. Okay, so number one, how about we draw a metal plate. Let's think of it as a rectangle, and well, we will impose some Cartesian plane here, and let's go to the point 2, 1, 2, 3, 2, -3. That's that point. So starting at that point, from that point we can go into pretty much infinitely many directions. Maybe so maybe the point where it's hottest or the temperature increases rapidly, it's this direction, maybe that direction, maybe that direction. We don't know. We will figure it out. Okay. So number one, what do we do? Find the gradient. In this case, it's nabla not of f of t in this case, and then the partial derivative of x with respect of the function t with respect x is -8x. And -2y with respect y. So that's the gradient. Now we want to know the gradient at the point 2, -3. So -8 times 2, -2 times -3. All right. So this means we have to go in the direction of the vector -16, 6. What does that mean? Okay, it means that from this point to -3, we have to move -16 units in the x direction and 6 units in the y direction. That is, if we go this way, that's where the temperature increases most rapidly. Of course, I mean, this vector that I draw in red, it's not perfect, it's not drawn to scale. It's just to give us a sense of direction. I mean, it's negative in the x direction and positive in the y direction, just to make sense of it. All right. So finally, let's get into climbing hills example. So we have one example of a hill whose shape is given by the equation z equals 1,000 minus 0.005 x squared minus 0.01 y squared, where x, y, and z are measured in centimeters. Okay, so we're standing at a point with coordinates 60, 40, 966. And the positive x-axis, so this is important, the positive x-axis points to the east and the positive y-axis points to the north. That is east, north. Well, if we extrapolated this, this would be west, this would be south, and well, this would be, you know, maybe underground. And I don't know, sky. Let's call it sky, all right? So those are the directions in this case. So the number one thing, so what are the level curves? So let's go back to look at level curves. So what's the shape of the level curves? Well, so recall that the level curves are given by some function f where z equals to some k. So, well, in this case, what we're going to do is set 1,000 minus 0.005 x squared minus 0.01 y squared equals to some value of k. So whatever that value of k. So let's get only the variable term. So let's subtract 1,000 on both sides. And well, what are we going to get? Number one, negative 0.005 x squared plus minus 0.01 y squared equals, well, k minus 1,000. It's just going to be another number. Let's call it c. And in this case, well, let's change these negatives into positives. 0.005 x squared plus 0.001 y squared equals still a c, because if we divide both sides by a negative, well, that's just an arbitrary constant, and it's just by absorption, the same way we did back in Calc 2 when we solved differential equations, if I remember that. Well, so in this case, what do we have? X squared and y squared. We have both variables squared. So number one, that could be circle, hyperbola, or ellipse. Well, hyperbola, definitely not, because none of those terms is a negative. Okay, so let's take that out of the option. So how about circles? Would that be circles? No, what would that be then? Ellipses, right? Because we have different coefficients or different, different denominators. So these are ellipses. So that means that if we were going around in circles, we will be walking elliptically, right? So those are the level curves in this case. Well, the question is, if you walk due south, will you start to ascend or descend? And at what rate? Well, from the picture. So let's go to the point again. What was the point? 60, 40, 966. So that'll be this point. Okay, so 60, it's in the positive x direction. 60, 40, and somewhere up right here. All right, from this point, just looking at the picture, I would like to go towards the south, which is in this direction. Looking at the picture, we will be going up or down? Up. Let's verify that using calculus. Well, so, okay, now, be very careful when they state the direction. Okay, so we need to walk due south. So essentially we want to find the the directional derivative because we want to find the sign of that value that is going to take us either up or down. Well, in this case, we're predicting that it's going to be up. And well, so number one, so let's see. We're going to go to the south. But again, because whenever we want to find a directional derivative, we need to make sure that we do it using a unit vector. So a vector pointing to the south, what would that vector be? Negative 1. Well, so the unit vector would be, okay, what's the x component of that unit vector? 0, negative 1, all right? So it would be in that direction. Now, so we have this unit vector, we have this function, let me write it down again. And so that's a z equals 1,000 minus 0.005 x squared minus 0.01 y squared. All right. So let's find the gradient nabla of z. In this case is, well, the partial derivative with respect x. Okay, so 2 times 0.05, that's going to give us negative 0.01. Or yes, 0.01 x, comma, the derivative with respect to y, so 1 times 2, that's 0.02, negative 0.02 y. So that's our gradient. So again, we're storing the information to get the rate of change in the x direction and the y direction, but we don't want the slope or the rate of change in either of those directions. No, we want it in a particular direction, in the direction, oh, well, actually it's going to be in the negative y direction because of we're going south, right? So let's see. So we need to evaluate the gradient nabla z at the point 60, which is x, comma 40, which is y. So that's negative 0.01 times 60, negative 0.02 times 40, and simplifying this, that should give us negative 0.6, negative 0.8. Okay? So, right? So let's find the directional derivative. So that is the directional derivative in the direction of u. That's going to be the dot product between the gradient vector, which is negative 0.6 comma negative 0.8, dotted with the unit vector, in this case 0.0 comma negative 1. Well, in this case, negative 0.6 times 0, what's that going to be? 0. And negative 0.8 times negative 1, that's going to give us 0.8. All right, so in this case, what does that value represent? We're going uphill, right? So that confirms our prediction from the picture here. Well, I mean, if we were to describe the units, because I mean, this is an application technically. Well, it is an application, not just technically. Well, we would have to write down the units, but in this case, everything is in terms of meters. So we're going 0.8 meters per 1 meter. So really, this will be unitless, right? So again, ascending. All right. Letter B. What if we walk northwest? What would be would it be ascent, descent, and whatever it is, at what rate? All right. Northwest, so not south, not north, not east, not west, northwest in this case. So number one, again, another picture. Cartesian plane and the direction of northwest. What would be the angle for the direction of northwest? Pi over 4 or 135 degrees. Well, so we need a unit vector in a similar way that we got the vector 0, comma, -1 to describe the motion in the direction of the sun, but in this case we need a unit vector in that direction. Recall that we can get that unit vector using cosine theta sine theta equals cosine 3 pi over 4 sine 3 pi over 4. Right, and in this case that's negative root of 2 over 2 comma root of 2 over 2. So that's the direction, that's the unit vector in the direction towards the northwest. So we're going to use the same calculation again. However, we don't need to find the gradient again because we already got it from before. So let's just use this information. So the gradient at the point 60 comma 40, which is negative 0.6 comma negative 0.8. Well, so let's find the dot product for the directional derivative, which in this case is negative 0.6 comma negative 0.8 dotted with the vector that we just found, root of 2 over 2 negative comma root of 2 over 2. Alright, so let's do this calculation. So 0.6 times negative root of 2 over 2, well actually negative, that's going to be negative. So for this I got negative 0.1 times the square root of 2 and plus, oh wait a minute, no. Let me do the calculation first. So that's a negative, so negative is positive 0.6 root of 2 over 2 plus, or well in this case minus, and 0.8 times root of 2 over 2. And if we do this calculation right here, initially I got negative 0.1 root of 2, which is the same as negative root of 2 over 10. Well, again, look, let's have a look at the sign of this value. What does that mean in this case? So we're ascending as we go towards the northwest, all right? So how about we look at the picture to see if that confirms it? Well, so from that point, if we go so north and west, we're going in this direction. We're going down the hill, right? It certainly appears we're going down the hill. All right. So let's relate this time. Oh, we're not done yet. There's a third part, right? In which direction is the slope the largest? So now we're looking in general, which is the direction that has the steepest ascent in this case. So if we're hiking along this, if we're hiking in this hill, well, what's the largest slope in this case? Well, so in this case, well, we got the gradient vector at the point is that 60 comma 40, yes, 60 comma 40, which is in this case, again, let me just rewrite it, 0.6 comma or negative 0.6 comma negative 0.8. Okay, so that is the magnitude of this vector would give us the actual value of the largest slope. That's negative 0.6 quantity squared plus negative 0.8 quantity squared. Alright, so 0.6 squared, that's 0.36 plus 0.64, that's the square root of 1 inside, which is 1. So rise 1, run 1, that's the steepest slope in this hill. So it's a good one to hike, I guess, right? It's not too steep. The smallest slope would be well, actually the one with the negative, even though they didn't ask for the steepest slope? Well, all we do is just change the sign. All right. Largest, lowest. Okay. All right. So what do we have over here? Well, so gradient and level curve. So again, another definition, another theorem. Well, so if f is differentiable at a given point x comma x sub 0 y sub 0, and the gradient at that point is not 0, then the gradient is normal to the level curve through that point. In other words, so if we have this level curve, that means that whenever the gradient is not equal to 0, well, notice how this gradient is pointing outwards, outside of that level curve. All right. So in other words, the tangent line to that level curve will be orthogonal. That is, it's going to form a 90 degree with with the other vector. Well, so number one, let's go back to review a little bit of level curves, and then we're going to put this together with the gradient. So we have this function z equals x squared plus 4y squared. Again, if we set the value z for different values of k to find different level curves, well, so they're asking us to find or to describe the level curve when z, well, actually z, not k. So 8 equals to x squared plus 4y squared. Well, if we divide both sides by 8, we should get x squared over 8 plus y squared over 2 equals to 1. Okay, what conic section is this? It's an ellipse again, right? So we have ellipses here. So we have an ellipse. For part B. Okay, for part B, they're asking us to, what are they asking us for? Find the gradient of the function at the point 2, 1 and sketch it on the level curve. Then find the slope of the tangent line at the same point and verify that the gradient is indeed orthogonal to the tangent vector at that given point. Well, number one. So let's compute the gradient. Let me write down the function again, so you don't go back to the previous page. So that's z equals to x squared plus 4y squared. All right. Well, so the partial derivative with respect x, isn't that a 2x? And the partial derivative with respect y, that's 8y. Right, so that's the gradient. Again, and we have the expressions in a vector to determine the rate of change in the x direction and the y direction. All right, now, so let's find that gradient at the point 2, 1. 2 times 2, 8 times 1. So that's a 4, 8. Alright, so that means that the rate of change in the x direction is 4, while the rate of change in the y direction is 8. So now we have it together in a single expression, stored in one vector. Alright? It's kind of weird how this is related to like programming, in databases, right? It's kind of unexpected. That's what I was thinking of it today, so... But it's interesting though. All right, they're also asking us to find the derivative of the tangent. All right, the slope of the tangent. Okay, so we need the function again, z equals x squared plus y 4y squared. All right. Notice in this case they're asking us the slope at the tangent, at the point where that is tangent. And they're not asking us for the slope in the x direction or the slope in the y direction. That we already did. So in this case, when they're asking us for the slope of the tangent, they're really asking us the slope at one single point. So what is this going to be then? So in this case, we will have to find the derivative of a single variable function. But wait a minute, that's not a single variable function. However, if we said, remember how big F of x, y equals z equals to 0? If we have big F of x, x squared plus 4y squared. So in this case, what are we going to do? We're going to take the derivative of this implicit function. Remember what we did last time? We reviewed how we got the implicit differentiation in Calc 1 and the new way to do the implicit differentiation in Calc 3. Remember how it was a lot shorter, and in fact, okay, number 1, dy dx equals negative the partial of f with respect x divided by the partial of f with respect y. But we don't really need to find these partial derivatives because we already got them from before, isn't it? So that's a negative 2x over 8y, which reduces to x over 4y. Now, to find the slope of the tangent, what do? Evaluate the derivative at the point, what was that? 2, 1. So let's plug in 2 for x and 4 times y, which is 1. 2 over 4, which equals to 1/2. That's the slope of the tangent. All right. That is, we have this ellipse. Let's not write the ellipse anyway. Okay. Look, okay, no, let's do it. So we have the point, what was that? 2, 1, and we have this slope, some ellipse here. All right. And we are going to have the vector 4, 8, and it's going to go in this direction. Recall that vector goes out of the level curve. Now, let's verify now that the vector, the unit vector in this case, did we get the unit vector? No, I don't think we got that unit vector. Oh, okay, how do we get that direction vector for the tangent? Yeah, that's a good question. Okay, this slope right here, m equals to 1/2. Recall that this slope is the ratio of the rise to the run, right? This is some delta x over delta y. Let me label this properly before showing what am I going to do. So delta x over delta y. And well, that's how we represent vectors when we write them in component form. The x component is basically the delta x, and the y component is basically the delta y from the origin when we write them in standard form. All right, so this means from here we can write this vector as the vector. Oh, that's upside down. Oh, again, come on. Yes, so that's going to be 2, negative 1. Where did I? Oh, I missed the negative here, right? Yes, so negative 1. All right. So in this case, let's find the dot product between this vector and that vector, shall we? And show that indeed that those are going to be orthogonal. So nabla f dotted with v, with this vector v, will be, okay, nabla f, which is 4, 8, dotted with 2, negative 1. 4 times 2 is 8. 8 times negative 1. And surprise, this is indeed showing us that the gradient vector is orthogonal to the tangent vector. All right, again, to get this tangent vector, we're going back to basically single variable functions, and I say it in quotation marks because really we have a multivariable function, but we differentiate this function like as if it were single variable function, but in implicit form. That's why we did implicit differentiation last time, to incorporate this with, with this gradients and all that. All right. Let's get to the last topic for this section, functions of three variables. So of course we can extend this to more variables, to three variables, and I mean the directional derivative is just the dot product of that direction vector A, B, and C with the components of the gradient, that is the rate of change in the x direction, the y direction, and the z direction. And the gradient is just add one more term. So, and again, well, I use the IJK notation, but so far I was using the component form. So that's this is what we were using for today's lecture. Well, all we do is just add one more component. All right. And well, the properties are exactly the same. I listed them here. Finding the maximum value and the minimum value. It's the magnitude of that gradient vector. The usual. All we're doing is simply adding one more component to our setting. All right. So let's do one example. So they're asking us to find the maximum rate of change of this given function f of x equals x squared plus y squared plus c squared at the point 3, 6, -2. And the direction in which this maximum rate of change occurs. So they're asking us for both things. Alright, so let's rewrite the function f as x squared plus y squared plus z squared to the 1/2. And let's find the three partials. We need to find three partial derivatives to get the gradient vector in this case. So, partial of f with respect to x. Well, so mini chain rule here. That's going to be 1/2 x squared plus y squared plus z squared to the 1/2 minus 1. But 1/2 minus 1, isn't that negative 1/2? And by chain rule, we multiply by the derivative of the inside of the parentheses, but in this case with respect to x. What's that derivative? 2x. Notice how the 2's cancel. Cancel the 2's. And at the same time, how about we write this using radical notation, but in the denominator, because number one, we have a negative exponent. So this will be x over the square root of x squared plus y squared plus z squared. All right, so that's the partial with respect to x. For the partial derivative with respect to y, this will be, again, 1/2 x squared plus y squared plus z squared to the negative 1/2. But in this case, by chain rule, we will differentiate the inside with respect to y. What's the derivative of? Isn't that going to be 2y? And see how it's actually going to be pretty much the same as before, but in this case with a y at the top. Okay, do you notice the pattern here? How about I skip all the steps for the partial derivative with respect to z, and in this case to z over here, and that's going to be simply z over the square root of x squared plus y squared plus z squared. So we got the three expressions, the three components of the gradient vector. All right. Interesting. So nabla f, that's the gradient vector. That's going to be x over square root of x squared plus y squared plus z squared, comma, y over the square root of x squared plus y squared plus z squared, comma, z over square root of x squared plus y squared plus z squared. So that's our gradient. Again, in this case, well, we're adding one more component to our database now to store one more piece of information, the rate of change in the direction of z. They're also asking us to find that vector at the point 3, 6, -2. So nabla f at the point 3, 6, negative 2. All right, so I don't want to write that whole thing. So notice the common factor or common term in our vector. So how about I will do this calculation on the side. The square root of 3 squared plus 6 squared plus negative 2 squared. And then I will just put it in the denominator of every component here. So number 1, so that's the square root of 9 plus 36 plus 4. And is that 49? All right, that's the square root of 49, which is 7, which is going to be really nice. Well, coming back to our vector, that's going to be 3 over 7, comma, 6 over 7, comma, negative 2 over 7. And so that's the direction, the direction we have to go in order to get the highest rate of change. And now they're asking us, what's that value of the rate of change? Well, find the magnitude of the vector. In this case, the square root of 3 over 7 squared plus 6 over 7 squared plus negative 2 over 7 quantity squared. All right. So the good thing, all denominators are the same. That they're going to be 7 squared, which is 49. 3 squared, which is 9. 6 squared, which is 36. 2 squared, which is 4. So again, 49 over 49. So 1 will be the largest slope in the surface for the point 3, 6, negative 2. All right.